Okay, so in the last lecture, we had started discussing the conservation of energy and the potential energy. We had defined the conservative forces. Conservative forces were forces for which, if you calculate the work done by this force from a starting point to the final point, the work done doesn't depend on how you go from the initial point to the final point. That is how we define the conservative forces. And once we have a conservative force, we could define something called the potential energy through this relation. Well, in general, when you are specifying such a quantity, such an integral, you have to specify how you go from point P0 to point P1. But for conservative forces, you don't need to make that specification. So this integral depends only and only at the initial point and the final point, not on the intermediate points that you take as you go from the initial to the final. So this integral can be just written as the difference of two functions which depend one only on the final point and the other one only on the initial point. And that is what we call the potential energy. So that is one key thing that we had done, define the potential energy. And once we define the potential energy, well, you can think of this potential energy as, in a sense, as the energy that you store in your system. So you see, this minus F is, if you consider this mass, it feels the gravitational force. It has a weight pointing downward. So if you want to carry this from this point very slowly, or with zero acceleration, let's say, from this point to this point, you do some work on the system, and you would like to you can think of this work that you have done on this system as the energy that you have stored in the system. So that is what this means. Minus F is the force that I am applying on this mass as I carry this thing from here to there. F is the force of gravitational attraction acting on this. I should apply the opposite of that if I want it to not to accelerate. So minus F integrated over the path just gives me the work that I do, and that is the energy that I store in my system. Initially, it had this much energy, if you just define it to be the initial energy of the system. This is the work that I have done. So this is the work that I have stored in my system, and hence this is its final potential energy. Now this combination, the kinetic energy plus the potential energy, is what we call the mechanical energy. And that was, okay, you have to think of the system when you are talking about the potential energy, because if you look at the definition, the force is the force exerted on my mass by other parts of my system. So if I consider its weight, then the weight is a force exerted on this mass due to Earth. So this thing over here, F, is something related with not with this mass, but with all the other parts of my system. Whereas this dl, the displacement, I am carrying this mass from here to there. So this mass is being displaced under the influence of the force created by the other parts of my system. And hence this definition, this integral, is a property of the whole system. So if Earth changes, then this force changes, and hence the potential energy changes. If the displacement of my mass changes, then the potential energy changes again. So whenever you think about the potential energy, you have to think of the potential energy of the whole system, not just a single part of my system. True. Well, we will calculate it. Okay, so this is the potential energy. Well, we will calculate it in a moment. We will see how to calculate it. Now, this is an important change that we are doing. We are studying the same system. We studied the motion of this mass before. We just threw it and considered it as a projectile motion. And now we are studying exactly the same system. before we used the velocity, acceleration, and the force, which were all vectorial quantities. So you were having all this tough time putting the vector signs, writing the vectors in terms of their components. Now, when we are talking about energy, remember the kinetic energy is 1/2 mv squared. It is just a number. This is my kinetic energy. It is just a number. It's not a vector. Plus the potential energy. It's again a number, not a vector. So we are now trying to describe the same system in terms of just numbers. So that's an important change. Well, we have the conservation of energy. And let's see. Now, of course, on one hand, we have this force. From the force, we could calculate the acceleration. From the acceleration, we could calculate the velocity at any time. And from there, we could calculate the position at any time. On the other hand, here we are saying that all the same thing can be done by the potential energy. So we are claiming that all this information is already contained in this energy. So one question is, if all the information is contained in that potential energy, how can we drive the force? So this information should also be contained there. So we should be able to obtain this force, which is a vectorial quantity, in terms of the potential energy, which is just a scalar quantity. And the way we do it, if you just look at the definition of the potential energy, you just imagine, take 2 points. Well, this is the difference of the potential energies between 2 points. This is the work done by the potential, by the force. If you just take it to move along the x direction only, the displacement is along the x direction only. So this is the potential energy at the point x plus dx, y, and z. This is the potential energy at the point x, y, and z. So the difference is equal to, well, if this is only has the x component, then the scalar product just gives me the x component of the force times the displacement in x. So I can calculate the force in the x direction. What I do is, I have this potential u, I calculate it at the point x, y, z. I calculated it at the point x plus dx, y, z. Look at the difference, divide by dx, and that will give me the force. But this should already be familiar to you. It is the derivative. If it didn't have the y and z arguments, it was just the ordinary derivative. But since now we are dealing with functions of 3 variables, this curly d just means that when you are taking this derivative with respect to x, assume that y and z are just constants. Just like 5, 6, they are constants. Do not take derivative with respect to that, but take derivative with respect to x only. So this is what this curly derivative means. And so, of course, you can calculate the y and the z derivatives. It will give you the forces in the y and the z direction. Now, this is just a shorthand notation for writing this whole thing. This is just a definition. Whenever you see this object, just know that it means this thing, this combination. And then we discussed already the how to interpret the potential energy diagrams. Because just by looking at the potential energy diagrams, we can extract lots of information about how the system behaves. One thing you should pay attention to is, if you look at well, this is just a one-dimensional example. The force in the x direction is nothing but the derivative of the potential with respect to x. Since this is a one-dimensional example, the potential depends only on x. It doesn't have the y and z dependence. So if, as you increase dx, if du is increasing, that is, the derivative is positive, then the force is in the negative direction. Now, if you look at all these points over here, as you increase x, the potential energy is also increasing. So the change in the potential energy divided by the change in x is positive. So along this line, the force is in the minus x direction because of this minus sign. So along this line, the derivative is negative. So the force is in the positive direction. It is always pointing towards this minimum. So in a physical system always behaves in such a way that it tries to minimize the potential energy. So if you look at this graph, you can immediately say that the system will always try to move either to this point or to this point, whichever one is closer. If I put my system over here, it will feel a force in the direction of the minimum of the potential energy, so it will start moving in this direction. We do not decide on where the potential energy is zero. We don't even need that. You see, if you look at the definition of the potential energy, in fact, we only define the differences in the potential energy. That is what we define. So the 0 point of the potential energy is not physical, it's irrelevant. You can just choose any point as your 0. You can just choose a point, an arbitrary point P0, and just say that at that arbitrary point P0, the potential is 0. But that is your choice. It is just like choosing your origin of your coordinate axis. You can choose your coordinate axis here, there, or there. The same is true for the potential energy. You can say that the potential energy at this point is 0, fine. Or at that point is 0. That's also valid. It's up to you. Yes. Oh, this should be P1, sorry. Here. Here you mean? Now this one is equal to this one, this integral. So this defines, you are right. This is P0 minus P1, and this is P2 minus, no. If you look at this definition, minus F is the difference of U of P1 minus U of P0. This minus sign makes the whole difference. So this integral, if you just move this to the other side, is equal to U of P0, the lower limit, minus U of P, the upper limit. So if you have an object, let's say, having this energy, and let's say initially it is at this point, exactly at this point, we know that its energy is equal to the potential energy. So it doesn't have any kinetic energy. It has 0 speed. But there is a force acting on it. The force is pointing towards the minimum of the potential. So it's pointing in that direction. So it will start accelerating in that direction. It will gain some speed until it reaches x0. Then that is where it will have its maximum velocity, maximum speed. Then it will slow down. It will reach its minimum potential energy at this point, kinetic energy at this point. Now it will accelerate, then decelerate, and then when it reaches this point, it will have 0 kinetic energy. So it will stop there. It stops there, but still there's a force acting on it, because this is not the minimum of the potential energy. So the force will be pointing in the positive x direction. So it will accelerate in the positive x direction, and then it will just turn around and move in this direction. So it started here, went to that point, and then it just turned around. So this point is called the turning point. It turned around, when it will go to this point again, and then turn around again, and it will just go back and forth. The motion will be periodic. It will never stop. It will just move back and forth between these 2 points all the time. Objections? You don't agree? You don't agree that it will go back and forth all the time? Okay. Well, these points are called the equilibrium points. These two are stable. This is the unstable equilibrium point. Okay, so what else we have? Now, of course, we don't always have conservative forces. We also have dissipative forces, forces which change the mechanical energy of the system, like the friction force, or in this case, the force of my hand is also one of these dissipative forces. It causes the energy to increase. The energy of this mass plus the Earth system is increasing. So this is also over there. It causes the change in the total mechanical energy. Yes? Sure. If you know how you are moving. Okay. Okay. Let's not complicate it to that level. Let's look at the friction example. I can integrate the friction force on a path. If you tell me which path it takes, I can integrate it over the path. If the friction force, the magnitude is constant, if I start from here, go over there, then the work done by the friction force, which will be the integral of the friction force, will be just minus the friction force times the displacement. I can integrate it. There's no problem with that. But if I integrate it from P1 to P2 along this path, and if I integrate from P1 to P2 along the other path, the two results will be different. You have to tell me which path you take, first of all, so that I can calculate that integral. But that means the friction force is not a conservative force. I cannot define the potential energy for the friction force. And this is how we define the potential energy for gravity. So we know the force. So we just imagine that, okay, I have, remember, potential energy is the energy of the system as a whole, not just a single part. So I can ask you this question. What is the potential energy of the system of these two masses? Just imagine them as planets in space. I have these two masses put at a separation r. So what is their potential energy? I need to calculate the work done by the system. First, I can, since the potential energy doesn't depend on which path I take, or you can say the same thing in other words, the potential energy doesn't depend on how you bring the system to its final state from its initial state. I will first fix a reference point. My reference point is when these two planets are infinitely separated. So they are infinitely separated. Then I bring one of them here to its final position. Well, there is no force necessary for that. That does zero work. Then I start bringing the other one from infinity to here. There is some work done by the force during this process. And that will be my potential energy. So if I brought one of them from infinity to this point, while I'm bringing the other one, this is a force that it feels. If I displace it by dr, the work done on this object by this force will be given by this quantity over here. Well, this dr, this is my planet that is fixed. I have the other planet. I have moved it very little. This vector is the dr vector. So the work done only depends on this change, on how the distance between the two changes, not on my displacement. Well, that is kind of nice because let's say if I do two displacements, this is the first displacement. This is the other displacement. So there is an amount of work done here, and then an amount of work done here. I can also imagine this path. I first do this amount of work, but that already tells me that this amount of work and this amount of work are equal. Then I go from here to there, but again, that tells me that this amount of work and this amount of work are also equal. So independent of how I go from this point to that point, the amount of work that I do is equal. That means that this force is a conservative force. So whenever you are trying to define a potential energy, the first thing you have to determine is whether the force is conservative or not. So this already tells me that it is a conservative force. If it is a conservative force, then I can calculate the difference in the potential energies between my point P and the point at infinity. Yes? Yes. Is the work that you have to do in order to make it to infinity. Yes. In hmm? No, because this is just a 2-point masses. In the exam, you have a huge planet. The solution is quite similar to this one, though. So there we didn't use the word potential energy, we used the word work, which we had studied before the midterm. So this difference is just minus the sum of all these works that you have to do, this potential energy. Yes? Yes. I'm bringing this one to here with 0 velocity. There is no force acting on it. No force. It is the other mass which should exert a force on this one, but the other mass is already at infinity. I'm just bringing one of them. I just give it a very small kick. It gains some velocity, and eventually it will reach this point. So there is no work done, no force acting on my system. Yes. You can also look at it like that, sure. The forces are always reciprocal, the action-reaction pairs. So if there is a force acting on this one, it should be created by some other object. Since there is no other object, there is no force acting on it. There cannot be any force acting on it. Well, we know how much work we need to do for a very small displacement. We just sum all the displacement until from when my mass starts at infinity, then it reaches the point P. If you take this integral, this is the potential energy of gravity between two planets or two objects. And this is the answer to your question. So if you have a variable force, what you do is you just divide it into very small segments of the L and sum all of them. And of course here we had chosen the potential at infinity to be 0. You could have said that the potential at infinity is 5, what's the unit? 5 joules. That's up to you. It doesn't make any difference. It will change the 0 of the potential energy, but besides that, it will not make any difference. From the integral? You can be quite creative. This is just the simplest way to solve it. Well, here what I have actually done is, here is my point P. Here is one of my planets M, and this is my target point. This is where I would like to reach. So I'm just assuming that my planet comes from this point, from a straight path from infinity. You can say that, okay, so it starts from here at infinity. It makes such complicated paths, goes around a few times, and comes here. You can calculate this work too, but I mean, what's the point? We know that whichever path we take, this is the answer we would get, because it's a conservative force. That is the definition of the potential energy. That's how we define it. Again, you can think of it like as if, okay, so where was the definition? Let's just look at the general definition. So it is this one, minus F. You can just say that, okay, the potential energy is negative the work done by the force as you bring your force from your reference point to the final point. Either you can define it like this, or you can say that the potential energy is the work that you have to do in order to bring your system from the initial point to the final point. because the force that you apply is negative the force that the system applies to that mass. So that's why you have this minus sign. And because of that minus sign, you end up having the kinetic energy plus the potential energy constant. If you wished, you could have defined this with a plus sign. In that case, the kinetic energy minus the potential energy would be constant. It's just for historical reasons, this is the definition. Okay, so then we had the escape velocity. So the question is, I have this planet over our everyday experience. The faster I throw an object, the higher it goes. That's what we observe every day. So is it possible? Well, of course, as the higher it gets, the gravitational attraction will be smaller. So its acceleration will be smaller, assuming that I can throw it to space. Well, mgh is the potential energy of gravity if g is constant. Yes, only close to the surface of the Earth you can use mgh. If you go to larger distance, this is what you should do. This is the potential. If I take this and throw it at a distance rp from the center of the Earth, this will be the potential energy of the system. Of course, for very small modifications, very small shifts, this will be almost linear. So remember, if you are, well, let's look at, take this example. The potential energy, it is minus Gn m divided by, suppose you are at a height h from the surface of the Earth. This is our potential energy. Now this I can write as minus Gn m small m divided by the radius of the Earth multiplied by 1 plus h over the radius of the Earth to the power minus 1. Now in your last homework, well, this is a very small, if this is a very small number. The radius of the Earth is around 6,000 kilometers. If h is just at most a few kilometers, then this is a very small number. And for very small numbers, 1 plus x raised to the power n is approximately 1 plus n times x. This is called the Taylor's expansion. Of course, it is infinitely, it goes until infinity. But for our purposes, this will be enough. So if you use that thing, this is equal to minus Gn m over the radius of the Earth, 1 minus h over the radius of the Earth. So this is just a constant. Well, you can just throw it away in the definition of the potential energy. What remains is nothing but mh times the remaining coefficients is your g on the surface of the Earth. Almost. Yeah, you see, the idea is this. If you have an arbitrary function, let's say like this, and suppose you know the function at this point, and you want to make an estimate of the value of the function at a very close by point. In this region, the function just looks like a line. If I consider this line, my function and the line, they overlap in this region. So I can predict the value at this point by looking at the value along this line. This is the first line approximation. It is valid for very small x's. Anyway, so this, if you are close to the Earth, does reduce to the MGH formula we had derived, but this is more general. For any distance, this is valid. So the question is this: what is the initial velocity of a mass should be so that it will be able to reach an infinitely far away distance? Now, if I throw it very fast, it will go to very high distances. If it goes to very high distances, the force that it will feel due to Earth will be very small. So eventually, it might be possible that there is a speed such that it will never come back. It goes up, and it goes up until infinity. Well, we can just write the conservation of mechanical energy. This is the kinetic energy, this is the potential. This is the kinetic energy at infinity, if it reaches infinity with infinite speed. Well, the potential energy at infinity is 0. So my initial speed has to satisfy this relation. Well, V infinity, we can say that, okay, what is the minimum speed such that it will be able to reach infinity? Well, the minimum possible value is when it reaches infinity with 0 speed, so that the escape velocity is defined as this value at V infinity equal to 0. It is given by this one. And just to put it on scale, this is the escape velocity of Earth, 11.2 kilometers per second. So what happens if the escape, well, if you look at here, as the mass of the planet increases, the escape velocity increases if you keep radius constant. Or if you keep the mass constant but decrease the radius, if you compress the planet, escape velocity increases. But eventually, you can reach a point where the escape velocity is equal to the speed of light. And what happens then? How did you relate that? Tell them. So, okay, you look at this expression. You increase the mass of the planet. If you increase the mass of the planet, the escape velocity increases. Suppose that the radius is constant. Or if you look at the other extreme, you keep the mass constant, but decrease the radius. You are compressing your planet. Then the escape velocity increases. You can have, keep mass constant. You can compress, let's say, Earth to such a small value. But it turns out that for Earth, that value is almost the size of an orange. It's just, let's say, 10 centimeters. If you compress all the mass of Earth into a sphere of 10 centimeters, then the escape velocity becomes the speed of light. You have a black hole because for an object to go away from that planet, that mass, it has to move at the speed of light. But we know that nothing can move at the speed of light. So nothing can escape that planet, including light. And you end up having a black object. What do you mean by penetrating the universe? Well, we didn't study Einstein. Okay, so let's discuss it later on, if you are interested. Well, of course, your friend has one point though. This we had derived using Newtonian gravity. And for black holes, Newtonian gravity doesn't hold. If you use general relativity, this factor of 2 is missing. That's the only difference, but the basic idea is still the same. Well, we had calculated the work done by a spring. From there, we can just obtain the potential energy of the spring. And the last thing we should discuss is the power. Now, this is kind of just a review of the things we did on Tuesday. Things that you should have studied at home so that we can discuss the questions in the class, right? Well, okay, we have the work, but usually we are not really interested in the work because work depends on how much, for how long you do something. If I carry this thing, let's say, okay, there is a friction force. I carry this book. There's a maximum power I can exert on it. So there's a maximum displacement I can create. So if I keep pushing it, I will do more and more work. So, but I know that I have a certain power. But that work is I have the power that the force that I can apply has a limit, but the work I can do doesn't really have a limit. So the work, if you want to quantify my properties in terms of the force, for example, the work doesn't really work. The important criteria is the work per second. Or you can just imagine this. Some of you came to my office. Just imagine that you went all the 4 floors in 30 seconds. So you know how you feel if you just go up 4 floors in 30 seconds. You will be just breathing heavily. Or you can imagine you go to the 4th floor in 10 minutes. Just slowly you walk up. And in that case, you wouldn't be tired. In one of the cases, you will be tired. In the other case, you won't be tired. But the amount of work you do in both cases is the same. You are going up the same height. So that determines how much work you have done. The work doesn't change, but the work per second in both cases is different. For the same work, if you do it in a less amount of time, then you will get tired. If you do it at a longer time, you will not get tired. So that is why we define a quantity like the power, the work done per second. Well, the work done, we know that it is the force times the displacement. If you divide it by the time it takes for you to make that displacement, you just get the power is nothing but the force times the velocity. Okay, there is this notation though. You have to pay attention. In general, there is no function W of time that you take the derivative of. Such a work function doesn't exist in general. What this notation means is that for your system, for the path that you have chosen, in a given amount of time dt, you do a work dw, and this is the power for that path at that instant. Well, the unit is watts. If you are paying your electricity bills, on it you probably see the notation kilowatt hour. Usually, the work we express in terms of watts. But of course, the work is watt, the power times time. So the unit of joule is watt seconds. You can say watt is joules per second, or joules is watt seconds, or if you like kilowatts hour. Okay, before we give the break, there is this question for you to think of. So imagine you have 2 cars. The volume of their engines are different. One is, let's say, 2 liters. The other one is 1.6 liters. Yes? They use the same fuel. 95 oktan. Okay, so what does that affect? So okay, that's an observation. So what is the consequence of that fact? Did everybody read the question, by the way, before you start answering? The question is this one. You have a car with a large engine and a car with a smaller engine. The car with a smaller engine, for it will be harder to go uphill. Küçük bir motoru olan bir arabanız varsa yokuş yukarı gitmekte epey bir zorlanırsınız. But for the car with a larger engine, it will be quite easy for you to go uphill. Now the trick to go uphill with a car with small engine is to use it at high rotations per minute. Küçük bir arabanız varsa onu yüksek devir hızıyla kullanırsanız da yokuş yukarı hızlanabilirsiniz. Why? Okay, so there is one answer over there. Why do you have much more power? Okay. Okay. So your friend is saying that we are increasing the rotations per minute. as we increase the rotations per minute, the power increases. So that is what your friend is claiming. But my question, first of all, why does the RPM affect the power? Why does increasing the RPM increases the power? Okay, let us continue with him. Okay, let's look at the definition of the power. Power is the work per unit time. Just compare this with velocity. It's quite similar. So if you are doing the velocity, it is how much you are displaced in a given unit time. So in the case of the, let's say my velocity is, I have a constant speed, I'm walking. Okay, in 2 steps, I will cover more distance, but my speed will not change. So you are on the right track, but I still don't agree with your explanation. That in 2 rotations, we are not producing more power, we are producing more work. We might be producing more work because we are considering 2 time units. 2 time units, twice the work, the ratio power is constant. So is that how the car works? Does it have a fixed work? That answer I liked more. Well, it is more or less where you were trying to get. If you look at so this is the definition of energy. That is the output power you get from some input power. Now, in the case of a car, the input power is burning the fuel. If you burn the fuel, you are inputting some power on the car. You are inputting energy to the system. Now, at each rotations, the amount of work you put in the car, the amount of energy you put in the car at each rotation is constant, more or less constant. So if the work is constant at each rotation, if you decrease the rotation time or increase the rotation times, how many times it rotates in 1 second, that is, you are decreasing dt. But for 1 rotation, the work done is constant, but dt, you are decreasing dt, so you are increasing the input power. If you assume that the efficiency is more or less the same, if you increase input power, you are increasing the output power. There is still one thing left to say. How is the output power related with the velocity you have, with the speed you have on the hill? Okay, we all have this feeling that if a car is more powerful, it will be able to go faster uphill. But what is the relationship? As physicists, we should be better. We should be able to do better than just having our intuition say that okay, it will go faster. How fast? What is the relation between the power output, let's say, and the maximum speed a car can have on the hill? Well, you have 10 minutes to look in your books.